Hi, my name is Brian Caffo, and I'm going to talk today about statistical linear regression models. And I want to emphasize the term statistical because in this lecture we're going to start talking about a little bit about inference. And this class is co-taught with my colleagues Jeff Leake and Roger Peng, and we're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so previously we talked about least squares, and our way of getting regression lines was really to think of it as a math problem, that I had a bunch of points in Cartesian coordinates, right? And I just wanted to find the line that minimized the sum of the squared vertical distances between the points in the line. But that's not a statistical model, okay? So why don't we try to formalize this with a statistical model? Why don't we say that our y's, our outcomes for person I or measurement I, is a line, beta naught plus beta 1i, then plus a random error term where the error terms are assumed to be IID, and it's not necessary to assume they're Gaussian for all parts of what we're doing, but we're going to frequently rely on Gaussianity of the errors. Now that's a much more that adds a lot of assumptions over what we've been thinking about previously, but hopefully we get something for that. This we think of this as sort of the sampling model, right? We're thinking that our errors are independently and identically distributed, and this is sort of the kind of mechanistic part. So as a consequence of this, what we wind up with is that the conditional expected value of the y's given the x's let me call that mu I, meaning that ith conditional mean, works out to be beta naught plus beta 1 xi, right? And that's easy to see because if I just take an expected value, I'm not going to write the conditioning on x part here. Expected value over here, since we're conditioning on x, all that part's none of it's random, so we have beta naught plus beta 1 xi plus the expected value of the epsilon i's, but those are 0 because of this assumption right there. Okay. The variance then works out to be sigma squared, which also you can see pretty easily. Variance of yi is exactly the variance of this equation, but all of that, we're conditioning on xi, which again I'm not writing. All of that is just a constant, so the variance of this whole thing is just the variance of epsilon because the rest of it's just shifting it around, okay, and that works out to be sigma squared, just again by that assumption. So this is equivalent, if we assume, now we're going to rely on our normality, if we assume that not only the epsilons are IID with 0 mean and variance of sigma squared, if we actually assume that they're normal, then this model right here yields the same likelihood as if we were to simply assume that the y's were normal mu I sigma squared and that the mu i's satisfied that relationship right there. Okay, so since we have a likelihood, we can do maximum likelihood. Let's write out our likelihood first, and hopefully you've taken the inference class. If you haven't, again, this class we're not going to focus on the mathematics, but for those of you who have taken the inference class, I'm going to show you some of the details. If you haven't, then maybe just listen or maybe skip a slide or two. We won't be quizzing or testing a lot on this kind of questions. So here's the likelihood. The likelihood is a bivariate likelihood, and it involves both beta, the slope parameters, which I'm concatenating beta as equal to beta naught and beta 1. So I guess it's a trivariate likelihood. It has the beta parameters and then the sigma parameters as well. But notice, okay, so as is often the case, we log likelihoods because this product's kind of annoying. So why don't we log it? And here by log I mean natural log. And then because of that guy and that guy, it's always good to take a minus twice the log likelihood. So maximizing the likelihood then is going to be equivalent to minimizing minus twice the log likelihood. Okay, and look at minus twice the log likelihood, then it turns out to be that guy right there. And, we're here again, remember mu I satisfies this guy. So if we want to minimize this equation with respect to beta naught and beta 1, where beta naught and beta 1 are embedded in this mu I right there. If we want to minimize it, notice it doesn't actually depend on sigma. And so if we can just minimize for beta naught and beta 1, that guy right there, we'll have minimized it overall, regardless of sigma. Now we'll have to figure out something else to get an estimate for sigma squared, but for beta naught and beta 1, if we can minimize that, then we're fine. Well, notice that's just exactly the least squares criteria that we minimized to get beta naught and beta 1 from before. So it turns out that under Gaussian errors, our linear regression model, the maximum likelihood estimates for the slope and the intercept are exactly the same thing as the least squares estimates.